So please help me in welcoming Vic and Michael. Please take it away.
Thank you, Timmy. Great. Can everyone see these slides? Perfect. Yep. So, good evening and welcome. Tonight we'll share our stories of how MIT Hyperloop came together to build an award-winning pod for Elon's competition, powered by sustainable energy and MIT innovation. Then we'll discuss future opportunities that our club can offer to the broader MIT community. Vic Parthiman will discuss the former, and I'll follow up with the latter. So without further ado, Vic Parthiman on prototyping and competition. Take it away.
Right, good afternoon, everyone. Good evening as well, and thanks, Michael, for the introduction, and thank you, everyone, for having us today. So, MIT Hyperloop has been part of the process for developing new technologies in the energy space around transportation specifically. And this is around the fifth year around the iteration of the Hyperloop program that was driven by Elon Musk and SpaceX. And MIT Hyperloop was part of the original design process for the competition, and then our team this past year was the second iteration of that prototype. And if you go to the next slide, Michael, the idea of a Hyperloop is to develop a high-speed frictionless system through an energy-efficient tube. And the purpose of this is to take you from, let's say, New York to Boston or LA to San Francisco in a span of 30 to 40 minutes. The meaning of this has a lot of possibilities. For example, you can imagine working from one city but living in another city. You can also imagine being able to commute to places that you may not be able to commute to otherwise on just a day trip. And that the purpose of this was to really drive, can we really look at a future economy where transportation no longer becomes a constraint to society? Can we travel to places and get work done without having to wait 2 hours or 3 hours in traffic? And so part of our team was to envision that concept, and we worked closely with SpaceX to make it a reality. Go to the next slide. So SpaceX and Elon Musk built a transportation tube about 1 mile long at SpaceX headquarters, and this still exists right now. And over the past 3-4 years, they've been having annual programs to test high-speed pods through these systems and see the capabilities and the scalability of such systems. So our Hyperloop 2 team, our second iteration of our prototype this past year, tried to demonstrate air levitation as a concept compared to magnetic levitation or wheels. We all know Maglev, the famous Maglev trains that run in Japan and Asia, but we want to try something different this past year and see, can we try a new type of levitation technology that's maybe potentially more energy efficient than magnetic levitation can be through these systems. And the purpose was to, again, test out this levitation system and really understand how energy efficient can it be in such a transportation architecture. And if you go to the next slide. This is our team. We had about 30 students this past year, both graduate and undergrad students who were involved in this project. We had several phases of the project. We were all from different departments of MIT, and such as system design management. We had MIT engineers from the chemical engineering program, from the electrical engineering program, from the media lab. We had folks from all over the university, all collaborating together to make this a reality. And again, we only were working with 6 months as a time frame. It's a very short time frame, and we had to build a pod within 3 to 4 months. So very, very accelerated in terms of the project, but we were able to pull it off. And if you go to the next slide, Michael. As you can see here, we started our second iteration of this prototype in September 2018, and we formed the team design, and around November 2018, we designed the first design package for SpaceX, and we developed ultimately around a 200-page document that detailed the entire subsystems involved, whether it's battery subsystems, whether it's levitation subsystems, pneumatics, electronics, and aerodynamic structures. All these things were part of the process for developing this prototype. And then we came up with the final design package, which we then submitted to SpaceX around January 2019. And then we had about 4 to 5 months to actually build it. And then we would take this vehicle to SpaceX around August of 2019, which is about a year ago from now. And to demonstrate the feasibility of this technology. And if you go to the next slide, this is what our vehicle looked like. So it's a bit different. It may look very different from typical vehicles you may see. We consider this as essentially a hovercraft. So this hovercraft essentially levitates on a bed of air. We built a portable hovercraft. You can see here, this one carries air tanks on there. And in the front of the hovercraft, there is a propulsion system, that's essentially an electric motor that drives this vehicle to about 200 miles an hour, from 0 to 200 in about 10 seconds. And we have a custom electronics built for this whole vehicle that controls the levitation system in the back, then a pneumatic system on the top, and then also manages the entire power management system as well. Our subsystems involved several high-power nanophosphate battery packs, and we also used polyurethane air bearings, polyurethane-coated air bearings for our levitation system. Our driving system was based on a high-voltage electric motor that operated around 400 volts and 200 amps. So we had nearly 80 kilowatts of power in the system. And the whole purpose was to understand, can we lift goods, lift weight? In this case, our vehicle was nearly 550 pounds, and this thing could be easily lifted by these air bearings. The air bearings could lift more than a couple of thousand pounds at least, and the whole purpose was to demonstrate a frictionless approach to travel. So you can essentially move this whole vehicle with your pinky if you wanted to when it's levitating on air. And given the distance of our track, SpaceX's track is about 1,300 meters long. So we had an acceleration distance about 1,000 meters and then braking distance about 250 meters. And so the whole purpose was to see how fast we can go and then brake in the given time that we have. And all on top of this, we also had to operate in a partial vacuum. And again, the vacuum really depends on sort of the, how fast you wanted to go. But again, we showed that at SpaceX that we were able to show, our air bearings working in partial vacuum pretty well. If you go to the next slide. So this is our team. We demonstrated our prototype at the MIT Museum once we built it. And as you can see here, we had a big group effort involved in this process. We had a lot of challenges to face and yet to face. Our battery pack had some significant revamps that need to be done. We actually, during our development process, had a small fire in our battery system, so we had to replace the entire battery pack of our vehicle. But this all contributed to a successful end journey, because when you're part of building a vehicle that no one has really built before, leveraging new propulsion systems, levitation systems, pneumatic systems, there's a lot that could go wrong. And so fortunately, we had a great team of really talented engineers that were part of this process, and we were able to build a vehicle on time and also ship it out to Los Angeles within the time frame that was given. If you go to the next slide, we had collaborated a lot with several team members that's from all over Boston, but also from Texas as well. And so we had a lot of collaboration involved, and we were working together remotely to really build this prototype. Our physical prototype was built in Boston, right underneath the MIT dome. But we had to do a lot of testing back in Austin, Texas. We had to do a testing in Los Angeles. And we had a lot of folks that had to fly in to build this vehicle during the last few weeks of the competition. So it definitely was a group effort. And as you can see here, this is the moment where we're putting the final shell on to the vehicle after we completed the new version of our vehicle design. And we had plugged in all of our battery packs, all of our pneumatic systems or levitation systems, and this vehicle is ready to be shipped over to SpaceX. And so this is at SpaceX. This is one of our colleagues, Patrick. He helped us design the pneumatic system. And this is him preparing the pod for acceleration in the Hyperloop. So basically, we were charging the vehicle, and we had to prepare the vehicle to be loaded with the air pressure. So we were operating with nearly 4,000 PSI of air. And we were essentially converting that PSI into about 30 or so PSI for the air bearing. So each air bearings took about 30 PSI, and nearly 10, I would would say SLPMs. In a way, the flow rate was a big contributing factor to see how fast we can go in this vehicle. So a combination of the airflow rate plus the pressure dictated sort of how much weight you can push, and also how smooth the friction, how smooth this vehicle is on the surface of the aluminum plates. As you can see here on the surface, there's an external subtrack that we loaded our vehicle to, and then we had essentially put the vehicle onto the internal subtrack, which was then loaded into the Hyperloop. So as you can see, here's a lot of steps involved. That tent behind Patrick was our command center, and so we had we're working together there to prepare our vehicle and to make sure that everything was going according to plan, preparing the battery systems, preparing the initial software launch protocol, and all the different procedures had to be in place in order for us to launch the vehicle. And so this is us finally loading the vehicle inside, and we had closed the tube. And then, about a year ago, we had launched this vehicle through the tunnel, and everything went really well. We had hoped we could have gone even faster. Unfortunately, due to the timeline and the restrictions of the competition, we had a lot of teams that were in line to compete. So we were at least able to test our air bearings, and they worked fine in the tunnel, in the Hyperloop, and there was no issue with the partial vacuum. And so one of the biggest takeaways was that we were able to design essentially an efficient hovercraft for this program. And so hopefully the next steps is to take that design further and implement some new ideas into maybe the third iteration of our prototype for this next year. And you can see here's an inside shot of our vehicle. You can see the air bearing sitting on the surface of the plate. You see the side stability wheel is making sure the vehicle is staying stable to the center of the track. And then essentially the entire vehicle would be levitating. You will see the diaphragm essentially expanding, and then the whole vehicle would be floating on a bed of air. And so this is a picture of our vehicle going through the Hyperloop. You can see here that the air bearings essentially expand a little bit, and then it gets ready to pop, and then it goes right through. Essentially, the vehicle then is fully autonomous, so there's no manual control of the vehicle. We all do that in the software itself. We prepare the pre-charge, all the electronics, and then they prepare the levitation, and then prepare the pneumatics, and then we hit go on the system. And there's a few lasers in the front that essentially monitor where we are in the tunnel and tell the system when to stop. So this is our team. Again, we were really proud of what we accomplished this past year. We won the Innovation Award at Spacex last year for this effort. And again, we see there's a lot more potential to really take this idea further. I mean, there's a lot of different technologies you can try with Hyperloop, but I think you might have heard of the recent Hyperloop One company who is launching a certification track in West Virginia. There's a lot of movement around Hyperloop all around the world. I think this is what we're doing here essentially is pushing the technology forward and bringing students and industry together to solve a problem. And as you guys may have heard of, the Boring Company is another company of Elon Musk, and they are working on building tunnels underneath the ground. And so the whole purpose is to build Hyperloops underground. And so we're also working with the Boring Company to determine and see the feasibility of a Hyperloop underneath the ground as well. And so this requires digging tunnels efficiently and also building a structure that would allow a future Hyperloop system to operate in an environment. And we're also thankful for our sponsors who are part of this effort. This is a big collaboration across both students, researchers, and universities and companies to make sure this was a success. So I think, especially with an endeavor like this, it's important to make sure you have a good team behind you. And I'll go ahead and let Michael take over the next stop. Thank you, guys.
And thanks, Vic, for sharing our story. It's quite a trip to those Innovation Awards. So I'll take it from here and discuss the future opportunities our club has to offer to the MIT community. So as Vic mentioned, Hyperloop has the potential to transform the transportation industry. And repeatedly, MIT has competed and we have won in Elon's competition or competitions. The latest iteration won Innovation Awards, in particular the Spacex Innovation Award, and the 2020 Edison Gold Award for Innovation in Next-Gen Logistics. So awards aside, we wanted to take this work one step further, and this is how we envision this next step. We demonstrated in our latest iteration that we can realize Elon Musk's original vision of Hyperloop, in large part by air levitation and partial vacuum. You can read his original white paper for the details. And of course, powered by sustainable energy for high-speed transport. So as an MIT club, we have demonstrated this. So what's next? One question that has boggled our minds is, what prevents a scalable implementation across the United States? This fundamental question becomes our focus and one of our new visions as an MIT club. We wish to tackle the fundamentals of Hyperloop, or Hyperloop transportation, and we believe that as an MIT club, we're well positioned to handle this. We dichotomize this research problem into two topics: engineering feasibility and techno-economic analysis. To unify this dichotomy, we propose a case study. What if we're interested in a path between Seattle and Atlanta? This path could provide potential socioeconomic benefits and jobs across the geographic regions. What then, in terms of engineering, is stopping this? We can address sustainable propulsion, human factors and safety, vacuum maintenance, and path infrastructure along this proposed trajectory. In terms of techno-economic analysis, we would have to address public sentiment in the US, the EU, and abroad, regulatory gaps, competition from other forms of transport, and how proofs of concept can support or stop a promising technology. So with this increasing specificity, we narrowed our gaze for the coming semesters on a specific problem. What in the fundamentals of Hyperloop transportation is limited by human compatibility? Or say another way, how does human compatibility constrain the propulsion and path infrastructure? We know that a human body can tolerate only so many G's in certain directions. How do the proposed trajectories interact or interplay with the human condition? And how does the latest in aeronautical engineering transfer over into this new space of transportation? And of course, the bottom lines. What is the final time to target? What are the finances involved? And what is the carbon footprint? So with this research in mind, we've been progressing as a club and found a new venue for our work while awaiting Elon's next competitions, in particular the Hyperloop competitions. Our sister schools in the EU have coordinated to create European Hyperloop Week. It will be a 7-day conference in which teams across the globe can come together and share their research and their innovation in this new sector of transportation. It will involve competition and conference elements, and more importantly, the ability to meet the leaders of our field. We also have another of Elon's competitions, not necessarily the pod, but for detunneling. And this is actually a substantial portion or contribution towards realizing Hyperloop. As you can see to the left in the company's own words, Hyperloop infrastructure may have to be built underground. So having a cost-effective tunneling machine would be quite important for this endeavor. So the competition rules are quite simple: fastest to target and most accurate to target. But of course, there's always room for innovation. As MIT engineers and business professionals, we can leverage our talents to push the boundaries of the state of the art. So right now, we're on the first tunneling competition, and we are submitting our design package soon. I'll give more details if you're interested in joining us. But our current prototype envisions using a conventional driller. Come to our meeting to the specifics, but augmented with the latest in machine learning and possibly with laser technology. Of course, we always need to have a venue. So on Saturdays, we have our weekly colloquiums. These are from 11 to 12 Eastern. Here we discuss current steps and next steps. And also, this is a venue to invite guest speakers who can give us their insight into the Hyperloop space. We have several members listed from the former team, all alumni, and a few have spoken, and we're working with schools across the US, the EU, and companies to see if they would like to participate in our colloquiums. So after all is said and done, what opportunities interest you? We've shown a few here, summarized on this slide, and increasing specificity in terms of research. We're actually arguably one of the first groups to look into the application of aeronautical engineering, such as G-force suits and passenger pod compensation. Many proposed designs focus entirely in this low G regime, but in order to realize one of the true benefits of Hyperloop at high speeds, we may need greater acceleration. So we are looking into sister labs in our campus that could help us realize this or bring Hyperloop to the next stage. Are you interested in hacking algorithms? Those are certainly of use for our work. And of course, AI, which has taken a hold through MIT. We'll in fact tell you a few ideas of how we can merge this for the tunneling competition. Of course, if you don't see a specific interest of yours here, please feel free to reach out to us and tell us what you have in mind. That way we can loop your interest and your talents into our team. And of course, we have the European Hyperloop Week to discuss our work and the boring tunneling competition. So if you're a mechanical engineer interested in building next-gen infrastructure, reach out to us so we can realize the tunneling machine together. Are you an ECS and have expertise in circuitry and controls? You're more than welcome. Are you taken by the craze in machine learning and artificial intelligence? This will certainly be useful in order to navigate our machine through pockets of potentially dangerous combustible gases. We've developed a spectroscopic technique in machine learning that could perhaps identify these gases and soil compositions, which would then inform how our tunneling machine operates to be the fastest to target and most accurate to target. So join us. You can see a subset of the current team here. You can use the QR code to the right to scan. I'll post a link shortly, and you can also reach out to us at the email below. Otherwise, welcome on board the Hyperloop team. Thank you. Hello, Timmy.
We can't hear you.
Can you hear me now?
Yeah.
Okay, perfect. And so now we'll be entering the Q&A portion of the keynote speech. If you have not already asked your question, then feel free to drop it in Zoom or Wova. And so one of the first questions we received was actually on the role of people in your team. So someone in particular asked, what would a chemical engineer be doing on your team? And so can you talk us through what different types of engineers or scientists or anyone else would do?
Sure, I could probably speak to this question best as I am a chemical engineer. So for a Hyperloop pod, chemical engineers are quite instrumental in determining the chemistry of the battery packs, and also for the tunneling competition, getting a better feel or quantification of the types of soil or geology in general. For instance, one of the algorithms that I've developed in collaboration with my PhD lab, we have a machine learning algorithm that can, well, identify spectra, infrared in particular, quite accurately and quite quickly. So your expertise in chemistry and machine learning can then be integrated into this tunneling machine. And perhaps very few tunneling machines that we know of actually use chemistry combined with AI. So I can speak that much for this question. If you'd like to add anything, go ahead.
I see a question here around air bearings. Can I answer that one, if that's okay?
Of course.
So the question was, does the air from your air bearings require more pump down of the tunnel? It's a great question. So one of the things that in the Hyperloop, if you looked at the specifications in the original Hyperloop white paper, is that when you're going at such high speeds in the tunnel, there's an air buildup that happens within the tunnel. So you have to have some form of a compressor regardless to be able to pump the air out of the front. It's almost like a syringe effect, and then use that air or either push it out the back or use it somehow. So the whole purpose is that in combined with that system, the air bearings would essentially be using that air that's being pumped through from the front. And so technically wouldn't necessarily need to pump down the tunnel just because you need support air bearings. The vacuum already the partial vacuum already is pumping down regardless, because the amount of air from the air bearings is very little compared to the amount of air you have to pump down for the rest of the tunnel. And again, this is a very isolated vehicle, right? Again, when you start adding in multiple vehicles, that equation may change. But in general, the air bearings also don't necessarily have to function in a full vacuum. They can also function in a partial vacuum or not even vacuum. And so you can think of it as just a system that can move heavy goods and more frictionless speeds. And so that's how I would answer that. The other question was, how would you address the requirement to maintain pressure in the passenger area, especially in the case of accidents? This is also a good question. I think in a full-scale system, you would have multiple interlocks or some ways to manage any kinds of pressure differentials. A good example is looking at sort of the London to the France tunnel underneath the ground. This is the tunnel that was built a few decades ago. Pretty large tunnel. There were two tunneling systems that were one from England and one from France that were building this tunnel underneath the water. And what's interesting is that when you're building such a system to accommodate passengers, you have to make sure there's enough vents involved for all kinds of pressure. And so even in a Hyperloop situation, if there's some form of an issue or a block down the road or down the tube, you would have to make sure that there is some kind of a pressure relief involved, either by redirecting the tubes to a different path or by essentially shutting down part of the tunnel and letting air fill the tunnel as well. So there has to be some mechanism involved to avoid any kinds of issues when there is a maintenance that needs to be done.
Thank you. That was a great response. There's also another question in what was saying, has there been a real demonstration of a Hyperloop? And how far is it from reality if it hasn't been?
I can answer this, but I think Vic can as well. Vic, would you like to go first?
Sure. Yeah, I think there has been some public, not with humans though. There has not been a passenger driven Hyperloop vehicle that exists today. That is the next big milestone. But there has been a full-scale Hyperloop track that's been built in Nevada by a company called Hyperloop One, or now Virgin Hyperloop, and they've demonstrated at nearly 200 miles an hour in that tunnel. Again, we also have the Boring Company building systems underneath the ground, but in terms of carrying passengers, that still is several years out. I would say, with the new certification track that's being built in West Virginia, they're expecting that to be done by 2025, and maybe passengers could try it or be part of that towards the end of 2025. But again, it really depends on the timeline for that certification track. But it is very critical to make a system that is capable of carrying humans. It's almost like building a space shuttle, right? It's a very complicated process, but you have to make sure a lot of safety procedures are in place.
Great. I'd like to add to that response. So that's actually where MIT Hyperloop hopes to stake a claim or stay at the cutting edge. So while many of our colleagues and contemporaries are investigating propulsion with non-biological goods, we're trying to investigate the next step while this change is coming into play. So how can we put people on board? And there's actually some interesting technology where aeronautical engineering, they have G-force suits. While this is not necessarily needed for maybe 2-3 Gs or below, if we really want to achieve the speeds that are being proposed in Hyperloop designs, we'll have to take this human factor into account. And we've also considered sort of tilting technology with levitation. We've seen this used before in different kinds of trains. In Scotland and Italy, they were trying to use their old tracks, but with high-speed trains. And so to compensate, they tried this tilting technology. And we're actually interested in how that meshes with this new Hyperloop with levitation. So we plan to remain at the cutting edge So that way, when this innovation takes place, maybe from MIT, we'll be there. Great question.
Yes, thank you. I think we have time for one more question. So, in Huva, someone's asking, what's the difference between maglev trains and the Hyperloop?
I also have an answer, but Vic, you can.
Yeah. So what's interesting, that's a very good question too. What's interesting is that when a Hyperloop first was sort of designed or conceptualized, Maglev was a technology that already exists, for high-speed trains, and so the purpose of Hyperloop was to make things cheap and energy efficient. And Maglev does have a lot of energy-saving ability, but at the same time, imagine putting a maglev train inside of in a vacuum tube, right? You're taking one expensive technology and putting in another expensive technology. So from the get-go, my opinion is that I don't think that's a scalable solution. And I think, there are other alternatives as well. I mean, even the Boring Company is not even using maglev. They're using just simple sleds, like electric sleds, to move vehicles underground. And again, it depends on how fast you want to go. Again, maglev is a very proven technology for high-speed systems. It definitely will work for vacuum systems as well. Again, the question really comes down to cost and how much you want to pay for such a